Welcome to this exercise session where we will be solving another strain energy problem. For this case, we need to calculate the deflection of a beam using Castigliano's first theorem. This problem, I will be going fast over the derivation of the shear force and bending moment equations. If you would like to have more details on the procedure to get them, I will leave a link to another video in the description here below where I showed how to do it. Also, in this case, we will be using Python to facilitate the symbolic calculations to solve the problem. And I think we are ready to start, and I have everything I need regarding data for the example. And one particular thing that caught my attention on this example, because, well, this is a simply supported beam with a point load applied at 3 meters from the end A, is that the specific details of the cross-section geometry are not given. The only thing that is given is that the product of the Young modulus and the moment of inertia is equal to 2 megapascals, if I'm not mistaken. Yeah, just to check that, yes, 2 megapascals or 2 million newtons per square meter. Now, I've written here the equations that we need to use. On the right, I have how much is the strain energy stored in the beam due to bending, and we've used this before, so it depends on the moment, the bending moment that is created by this point load. But now, if we want to apply the Castigliano's first theorem, what we need to do is to partially differentiate that strain energy with respect to the load, and then evaluate along kind of the length, of course, after the integration processes, and then you would get how much is the deflection of the beam. So let's start doing that. Let's go back to Python. So here I have the same figure that is presented in one node here on the right. And the first cell here is just to import the libraries that I need to use. So Python helps me to do all of this stuff. So I'm going to run this one. And I have the virtual environment activated and everything. So everything is good to go. So we just need to wait until this runs. I don't know why it takes so long in this case. It's just importing the libraries, but it takes some time. Again, I'm not going to be commenting too much. I'm going to write the comments on this part, and whatever detail that needed to be expanded, I would use one node for that. So first, again, I need to define my symbolic variables. I define the symbols. That's correct. And I'm going to use, let me check the figures. I'm going to use P. Even though we have a value, I'm going to use it as a symbol because I need to differentiate partially with respect to it in the future. So at some point, I need to keep it as a symbol. I'm going to have the reaction forces at A and B. I'm going to have X because X is the variable on which I'm going to integrate to obtain the strain energy. Let me see what else. I'm going to leave E and I as also symbols. And then I would search to substitute the product of E and I by using this value. But okay, let me use those. So I'm going to use X, or A, or B. We said P, we need to use it. We need to use also E and I. Yes, I think those are the cases. There it goes. Perfect. Great help from Copilot. Let me execute this one. And then, again, I need to formulate my shear force equations. Then I need to formulate, using the shear force equations, the bending moment equations. And that's what we're going to do. But first, we need to find out what are the reactions that I don't know, reactions in A and reactions at B. So let me write here then, reaction forces. Sum of forces in Y equal to 0. That is it. So I'm going to say that sum of forces in Y. So I'm going to call this sum of forces in Y equal to, well, yes, if I consider that reactions in A and B are positive and force P is negative, that's correct. And then I need to formulate the force equation that is equating this equal to 0. And then I can print this to see how it looks. And there it is. Pretty similar to the previous example. Now we need to take moments with respect to A and make that equal to 0, so we can have another equation and find out the values of the reactions at A and B. So taking moments with respect to A, so then MA equal 0. Put a dot here. Then I'm going to have, let's see, if I'm standing on A, then the moments are going to be MA is going to be equal to minus P times 3 meters. I don't need to do any change. Plus RB times 4 meters. Yes. Then I need to find the equation that I need to use to solve the system. Yes, then let me print it out to see how it's looking. There it is. Perfect. Now let's solve for RA and RB. by using those two equations. And I'm going to call it like this one here. So I'm going to solve using these two equations, the force equation and moment equation. I'm going to find the values of reactions at A and B. Perfect. And then if I just print out those just to check them. Awesome. So I'm going to have that reaction at A is equal to P divided by 4, and reaction at B is equal to 3 divided by 4 times P. Makes sense. So B is more loaded than A in this case. Perfect. Now that we have found the values for the reactions at A and B, yeah, they look good, but I would like to put it into this form. So let me just take what's the value of RA. Yes, and then the value of this one. Yes, and let me just verify that I'm getting what I need to get. Yes, this is RA, and this is RB. Perfect. Then let's write down the shear force piecewise function. Yeah. And this is part I'm going to just fly over because we already did it in another exercise where you can check it out, and all the details are very well presented there. So I'm going to have this one here, and yeah, so it says that before 3, RA is the one that's going to be active, and then from 3 to 4, I'm going to have this one that is correct, and then this is V, but I could have, let me see how it looks like. Awesome, yeah, it looks pretty good. But now, as we want to plot this value, I'm going to use VVal, and that's going to be V, and that's going to be substitute. No, I just need to substitute P, and P is 50 kilonewtons, like this. Then I can say that VVal is this one here. Perfect. This is perfect. Now we can plot. I don't know why it comes this error like this. But let's see then. Plot shear force diagram using the built-in function given in SymPy, and then that's going to be this one from yes, but I want to plot it from 0 to 4. And why is not giving me any more labels or something like that? Let me see if I can write some labels here. Yes, this is the one I want. And title should be enough. Perfect. Let me see how it comes. And there it is. So we have, I assume, about 12,500 newtons here, and I have 37,500 newtons on the bottom, and all crossing at 3 as it corresponds to this chart here. Perfect. Now let's find the moment, the bending moment, by integrating the shear force. By integrating the shear force. Yes. And that's going to be a simple, I can call it M equal to, let me write it from integrate function of X, because this is a method it has. This is perfect, and then I can plot M. Now, this is interesting because this is important to do it in this way, because if I make a change here at the beginning of the problem, then everything is going to be automatically updated here. So let me see what comes up. Oh, this is perfect. Look at this. So awesome. For X smaller than 3, we're going to have this. Then from 3 to 4, I'm going to have this. Yeah, this should have another condition, kind of explicitly saying from 3 to 4. We can force it out, but it's going to work in this way. No, not a problem. Now let's plot the bending moment diagram. Yes. Now, I believe I should have diagram a M value. That's the one I'm going to plot. That's going to be M, and I'm going to substitute P equal to 50 kilonewtons, because we can see here that the moment is just in function of this one here. So I could try to write actually this display in a better way. Let's see what comes here. Math, and I can write here maybe R something. No, I don't want this. I just want to have, just bear with me, I'm trying to write this in here, plus latex, maybe M. Should it work? Yes, it is. It works. Perfect. This is a way to do it. And here I have this, and then let's make the plot. Let's be plot, and let's be lazy and leave Copilot do it for us. And here it is. Want to plot this equation, or not, this involve the value of M when I substitute all P in this one here from 0 to 4, and this is perfect. So let's run this. And here it is. Look at this. It goes ascending up to 3 in X and then descending up to 4. Perfect. Now that we have the bending moment diagram, what we could do is to calculate the strain energy G calculation. And we have the formula here on the right, so it's this one here. And then after having that, what we need to do is just partially differentiate it with respect to p. So let's do that. So u is going to be equal to the integration, integrate what? Let me see. I could put, no, this is going to, I could put something like this. First, before everything, I'm going to have this fraction, which is 2 times e times I, and here I don't know how much is this e and how much is I. I just know that the product, again, as I mentioned, product, I know that is 2 megapascals, but I don't know how much individually are they, and then this is going to be what then? M to the power of 2, and then I'm going to integrate that in x, and that's x is going to go from 0 to 4, like that. And let me plot it to see how much it gives us. Look at this. 3p squared divided by 8ei. Perfect. Okay, let me just display it in a better form. Display, and then we can have it nicely like this. Yes, and then deflection of the beam. We know that we need to partially differentiate this previous equation found, and we're going to call it delta. And let me see, delta. This is a problem, so it goes so fast, but this is not what I want to do. I just want to differentiate strain energy with respect to P. I want to plot it, or I just want to put it like this, display the delta there. Let me see if it gives me the, yes. Let me see, and here it is. So the deflection is 3 times P divided by 4 times E times I. And let's find the value, because that's the question they're asking. So value of the deflection, sorry about this, deflection, and we're going to call it delta value. Let me see, it's not responding my computer, so delta value. Yes, so we're going to substitute P, but I don't know how much are these, but I do know that this times I, this is the beauty of symbolic Python, is that this is equal to 2e6. And then I can plot this value here. Here it is, and this is going to give us the answer in meters. So this is 18.75 millimeters. Nice, nice. And we have found the answer for this problem. Look at this. This validation worked fine. This validation also worked fine. So we are all set. So we used Castigliano's first theorem to calculate the beam's deflection, this simple example. And yeah, 18 millimeters, 18.75 millimeters. In meters. Excellent. All right. So let's stop here and let's continue with another problem. Thank you for being with me up to here. Bye.